All right, so we're going through the first 5 multiple choice questions of Unit 2. So on the basis of electronegativity difference among atoms, which of the following scientific claims is the most accurate regarding the bonding in magnesium nitrate? Okay, and what'd you get, Rainisha?
I was thinking between C and D, and I ultimately, okay, never mind.
No, but you just can't. You shouldn't be thinking between. You should know.
Oh, well, I was gonna say D, but
Yes, absolutely. So nitrate's a polyatomic anion. So yes, D is correct. Is that what you got, Caton?
Yeah, I got D as well.
Exactly. At this point, we just need to know that nitrate is a polyatomic anion, and that it's going to bond to magnesium 2+. Very good. Okay, we're going to need 2 of these guys because they have a 1- charge. All right. Which of the following claims about a binary compound in which the bonding is ionic is most likely scientifically valid? Okay, Caton, what'd you get?
Okay, that one I got D. The electronegativity difference is relatively large.
Yeah, exactly. And that's that's between a metal and a non-metal, and there's always a huge electronegativity difference. Is that what you also got, Rainisha?
yes.
Very good. We're moving on. Which of the following claims about a binary compound composed of elements with the same electronegativity is most likely to be true? Okay, what'd you guys get?
I got B as in boy.
You too, Rainisha?
I did as well.
Perfect, yep. And that's just the definition of nonpolar covalent. The 2 elements have the same electronegativity or very similar electronegativities. For instance, carbon and hydrogen, right? Slightly different, but so similar that we just know that they're going to be nonpolar covalent when they bond to each other. Their bonds are going to be nonpolar covalent. Okay, so molten sodium chloride is represented by this diagram. Which of the following indicates whether this liquid sodium chloride will conduct electricity and best explains why or why not? So what'd you get, Rainisha?
I was thinking D.
D, it does not conduct electricity because there are no free electrons. Okay, and what'd you get, Caton?
I got B. The ions are free to move.
Yeah, so if you look at this one, right? So these ions can move around, okay? So they're moving around, and as long as the ions are able to move, the material can conduct electricity, okay? So B is correct. Great, okay. And then number 5, what'd you get here, Rainisha? The particulate level diagram shown above best helps to explain which of the following properties of ionic solids.
I said D.
D, conductivity. Okay, do ionic solids conduct electricity? Do they have mobile ions? If you look here, right, like these ions can move around, but think about a solid. What do we know about solid? Right, that they're stuck in place. Okay, so they're not conductive. So what else might they be? What's happening? What's going on between these layers? What are they doing?
They're repelling.
They're breaking, right?
Yeah. Oh, so brittleness.
Brittleness, yep, exactly. Is that what you got, Caton?
Yeah.
Okay, very good. I'm going to go ahead and pause the recording, and now we'll do the next 5 questions.
For this problem, I actually, I got C.
Okay, so let's look at the specifications, right? Maximize attractions, minimize repulsions. So like charges repel, opposite charges attract. So here, like this positive is surrounded by negative, right? And so is this positive, and so is this positive. Same thing, this negative has 2 positives, and it's only going to interact at all with 1 negative. So that's pretty good minimization of repulsion and pretty good maximization of attraction. If you look at C, right, like these positives are right next to each other. So that's a problem. Okay? So that's why, like, and all the other ones in the negatives are next to each other too. So no matter how close they might be together to like positive to negative, like they're still close to other like charges, and that's the issue. So yep, A is correct. And then we're gonna move on to number 7. Which of the following indicates whether the solid substance represented by the particulate diagram shown above conducts electricity and explains why or why not? Okay, what do we think?
I ended up getting B for this one.
Got B as well.
Yeah, that's right. You can see that the electrons can just move right through. What kind of material is this, guys? What do we think this is?
Some kind of metal.
Yeah. So in a metal, the cations or the positive nuclei stay in place, and the valence electrons are free to move about the material. Okay? All right. Which of the following particulate level diagrams best represents an interstitial alloy? Okay. So what did you get here, Caton?
I got A.
A, what'd you get, Rainisha?
I got A as well.
Yeah, those are called interstices, okay? Those little spots in the middle. Very good, interstitial alloy. All right, and what's going on here with this metal, okay? Rainisha, tell us.
I got D.
Form substitutional alloys because it shows how atom of two different metals. How would you distinguish that there are different metals here?
Yeah, that was what I was thinking as well, but
I don't see that. I don't see
yeah.
that. I don't think it can be D. Okay, what else could it be though? What are these two
could
layers
be,
doing? What now?
It could be B.
Yeah, malleability. Good. So the two different layers can move relative to each other without losing their contact with the electron C. These are malleable. These are malleable. Very good. Okay. Very good. Very good. The same thing also happens in ductility when the metal is drawn into a wire. Okay. So either answer would have been correct, but we didn't have ductility as an option. We only had malleability. Very good. All right. Last one, number 10. What did we get for this guy? Diagram 1, diagram 2. Which one best represents the formaldehyde molecule?
I got C for that one.
C, because it's trigonal pyramidal. This one, I don't see this guy. This guy, I wanted to say that too at first, but it's not. This thing's not trigonal pyramidal.
It's
this thing's
planar.
trigonal planar. Yeah.
Mm-hmm. Yeah, I got a
little brutal.
I got diagram 2 because of the formal charge.
Yeah, that's right. Diagram 1 is wrong because oxygen has a -1 formal charge and carbon has a +1 formal charge. So these two aren't happy, but these two are. These two are happy here. So yeah, D is correct. That's really tricky. Do you see that now, Rainisha?
Yes, I do.
Yeah, that was really tricky. And do we need to do a review of calculating formal charge?
Really briefly, so every electron on a given atom counts as 1 and every bond counts as +1.
Okay.
And then if the net charge is equal to the number of valence electrons the element has, it's got a formal charge of 0. If it's greater, it's got a negative formal charge, and if it's lesser, it's got a positive formal charge.
Okay. So number of valence electrons, right? Formal charge equals number of valence electrons minus, okay, number of bonding plus number of lone pair electrons, okay? Right. Minus the number of lone pair electrons. That's correct. All right. So it's the number of bonding electrons plus the number of lone pair electrons subtracted from the total number of valence electrons, okay? So like, let's look at oxygen here, right? Oxygen has 6 valence electrons minus 2 bonds, it shouldn't say number of bonding. That should say number of bonds, not bonding, but number of bonds plus number of valence electrons. Number of bonds, okay? So minus 2 bonds plus 4 lone pair electrons, 4, okay? That equals 0. That's a happy oxygen. Whereas this guy over here, he is 6 minus 1 bond plus how many lone pair electrons, Rainisha?
I'm sorry?
How many lone pair electrons do you see here on this oxygen?
4.
The one I've just circled, this one here.
The one on the left?
Yeah. How many lone pair electrons?
6.
Right. So if you do 6 minus 1 plus 6, right, you get 6 minus 7 equals -1. So that oxygen has a formal charge of -1. So that's not a happy oxygen, okay? I mean, oxygen's okay like that, but it's not as happy as the oxygen with a 0 formal charge. Atoms generally want to have a formal charge of 0 in compounds, okay? And when we construct compounds, we want to minimize formal charge. All right, do you guys want to do let's do this. So Rainisha, calculate the formal charge of this carbon versus this carbon. And then Caton, calculate the formal charge of the hydrogens, okay?
Okay.
All right, so go ahead. I'll pause the recording briefly. Take a couple minutes to do that. Okay, so we agreed that this carbon has a formal charge of 0. Why? Because 4 valence electrons minus 4 bonds equals 0. Okay, 0 formal charge. This carbon has a formal charge of +1. Why? Because 4 valence electrons minus 3 bonding electrons equals +1. Okay, that's the formal charge on that carbon. All right, and then Caton says hydrogen, 1 valence electron, 1 bonding pair, 1 minus 1 equals 0, happy hydrogen. Okay, very good, Caton. Thank you. And Caton, do you have any questions about what we discussed?
No.
Okay.
It took me a second to dig back and figure out how formal charge worked, but once I remembered it was pretty simple.
Yeah, that's exactly it. It takes a second, right? Like when you're going back through at this point in the year, you have to remind yourself, about stuff that we studied in, like, we probably studied formal charge in, oh, I don't know, September or something. So it's
Yeah.
All right, number 11. Based on formal charges, which of the following is the best Lewis electron dot diagram for H3NO? Okay, so what's going on here? The best Lewis dot diagram for H3NO based on formal charges. What do we think? So what did you pick, Caton?
I got A.
You got
that's
A.
the one there where
Okay.
everything seems to have a
And then
formal.
Rainisha, do you want to take another look at it now that you're a little more comfortable with formal charge?
Yes, please.
Okay, take another look at it, right? So let's look at like some of these together though. So let's look over here. So first off, does oxygen make 3 bonds?
Not if it
No.
can afford
Not
not to.
typically, right? And so let's calculate the formal charge of that oxygen, okay? So oxygen has how many valence electrons?
It has 6.
Good, Rainisha. Did you get that by counting, or did you come up with the electron configuration?
I did it from counting.
Good, good. That's a great way to do things. That's how I always do them. Good. If we did the electron configuration, we would see 1s2, 2s2, 2p4, 6 valence electrons. That's how you get them from the electron configuration, but counting is always the quicker way. Okay, so we're still talking about this oxygen over here, right? So it's got 6 valence electrons, and then how many bonds does it make here?
It's making 5 bonds.
No, not
Oh
5.
no, it's making 3 bonds.
There you go.
Yeah.
And then how many lone pair electrons does it have?
2.
Okay, and that equals what?
0. No. 1. Positive 1.
There we go. Okay, so that's the formal charge on that oxygen. Is that oxygen happy?
No, it is not.
No. Now let's take a look at A, right? A. So if you look at A, what about this oxygen? Is this oxygen happy?
It is happy.
How do you know?
Because you take 6 valence electrons minus the 2 that it's being bonded to, or the 2 bonds it makes, plus the 4 lone pairs, and 2 plus 4 is 6. 6 minus 6 gets you 0.
Very good, Rainisha. Okay, and then all we have to do, guys, is calculate the formal charge on this nitrogen. Is this nitrogen formally charged? If so, how? So go ahead and just take like 30 seconds to do that one, okay? Or do you want to just take me through it right now? Caton, do you want to take me through since Rainisha did the last one?
Yeah, sure. So it's got 2 bonding electrons, 1, 2, and then 3 bonding pairs. So 2 plus 3 is 5, and nitrogen has
You mean
5
2 lone pair electrons?
Yeah.
Okay, go ahead. And then what now?
So that gives it a net charge of, so it has 5 valence electrons, and 5 minus 5 is 0, so it has a formal charge of 0.
Yep, that's right. That's exactly right. Okay, is that what you got too, Rainisha? Do you see that one?
Yes, I see that one.
Yeah, good. Okay, so Rainisha, how are you feeling about formal charges now?
Pretty good.
Yeah, I think you're going to be just fine. This is one of those topics you absolutely crushed the first time through. It's just been a while. Good. Okay, so let's move on to number 12 here. All right, diagram 1, diagram 2. Okay, which of the Lewis diagrams shown above is the more likely structure of CO2 and why? All right, so now we should be able to see this, right? Be able to see which diagram is better and why. So just take a quick look. I'll just kind of pause for 5 or 10 seconds here. Okay. And then what do we think, guys?
All right. It's going to be diagram 1.
Okay. And why do you think so, Ranisha? Because the double bonds are stronger than triple bonds, or because all of the atoms have a formal charge of 0?
I was gonna say B, that double bonds are stronger than triple bonds.
So
Or is
actually,
it the other way around?
triple bonds are actually stronger than double bonds because you
Yeah.
got 3 bonds, right? So a triple bond is stronger than a double bond, which is stronger than a single bond. That's true. But look at the formal charges, right? What's the formal charge, Ranisha, of the oxygen here, which is identical, by the way, to the oxygen over here? What's that formal charge?
Oh, it's 0.
Yeah. What's the formal charge of this carbon?
0.
Yep. So A is correct, right? But
Yeah.
let's take a look at the other diagram just for kicks. What's the formal charge of that oxygen?
It is. Is it -1?
Good. And what about the formal charge of this oxygen?
Is that one 0? Or is it 1?
+1. Very good.
Yeah, okay, 1.
And then what about this carbon?
Is that 0?
Yeah, it's 0, right? 4 minus 4 is 0. Very good. So what you see here is you have +1, -1. You have these formal charges. That's not stable, okay? Whereas these are 0 and 0. That's stable. This is a better structure. This resonance structure could occur for some, fleeting amount of time, or fleeting proportion of time, small proportion of the time for carbon dioxide, but it's not a stable structure. It goes away extremely quickly. So this is the regular structure here. Okay. Very good.
Yes.
All right, let's take a look at number 13. Have we oh, we did this one. Oh, I see. So I just started moving us through. Oh my gosh. Okay, so we haven't even seen these yet. We're just doing okay. Let's do. I'm sorry. So I forgot that we were stopping at 10 and we were just going. Now we're like going through them one by one. Okay, you guys need time to think through this stuff. All right. I'm sorry. I thought these were questions we'd already done this morning. Okay. So good, very good job. Okay, to be able to solve these on the fly. All right. So we've got 13, 14, and 15. Okay. 13, 14, 15. Let's take 3 minutes to do those. Okay. 3 minutes to do those problems, and then I'll check in after 3 minutes. Does that sound good?
Mm-hmm.
Okay. Hey Siri, set timer for 3 minutes.
Okay. Your timer is set for 3 minutes.
Okay, so we're talking now about question 13, and we've said that B and D cannot be polar molecules because they're symmetrical, right? And you can see that right there. You can see that these are linear molecules that are symmetrically arranged. So they can't have net molecular dipoles, which is required for polar molecules, okay? By definition. But then this BF3, it might look like it's asymmetrical. It actually isn't. It's just that the Lewis dot diagram is drawn in a T shape by convention, but actually represents this trigonal planar molecule. So BF3 is also symmetrical. So that is not a polar molecule. So the only one that can be polar here is C. And we have to represent that this way. So we'll use our pseudo 3D diagram, right? So we'll have our two CLs, okay, in the plane of the board. And then we'll have one H going back out, okay? And then another H coming out toward us, okay? And what we see here is that this side of the molecule on the right is taking electron density away from the middle of the molecule. So we're gonna have a partially negative side over here, delta minus, and we're gonna have a partially positive side over here, delta plus. Okay, any questions about that, scholars?
I'm good.
Okay, very good. So that's the scoop with that molecule. All right, number 14. Okay, Ranisha, get us started. Which of the following correctly compares the strength of the two carbon-to-carbon bonds in the molecule represented in the Lewis diagram above?
When I was looking at this, I was thinking about how this carbon-to-carbon is a double bond and how the other two were that was a single bond.
Yep.
So I was assuming that that a double bond is greater than a single bond, thus
Yep.
me picking A.
That's right. Double bonds are stronger than single bonds. That's that. Any questions about that?
Mm-hmm. Or no.
Good. Peyton, you got the same thing, correct?
Yeah.
Very good. Okay. And then number 15. Based on the Lewis diagram for ammonia shown above, the H in H bond angle is closest to which of the following? Oh, okay. This is a very interesting one. So what do we think, guys?
This is.
I was confused on this one because I
Yeah.
didn't know which H and H it was
Yeah,
talking about.
you have to draw the thing right, and then you say to yourself, okay, there's like an H in the plane of the board, there's an H coming out, and then there's another H back behind the board, right? And that's a trigonal pyramidal molecule. And the electron arrangement, or the arrangement of electrons, right? Electron groups. So we got this lone pair on top, and then we've got this bond here, and bond there. I'm going to uncircle the bonds. The electronic geometry is tetrahedral, and we know that the tetrahedral bond angle is 109.5 degrees. That's what that question was getting at.
Oh,
Okay. So when it's HNH, it's like, what's this angle, or this angle here, or like this angle in the back, and they're all roughly 109.5 degrees. They're actually going to be a little smaller than that because this lone pair is going to push them down. It's going to exert a repulsive force and push them down. So they're going to be a little narrower. I don't know, maybe 107 or so. Something like that, okay? You can Google the actual bond angle, but it's going to be closest to 109.5, which is the ideal tetrahedral bond angle. All right. So may I erase the board?
Mm-hmm.
yes.
Yeah, this is kind of a nasty one because it requires that you not necessarily memorize, but kind of memorize.
Yeah. I was only going to get that because of memorization. I wasn't going to get that from any other for any other reason. I mean, you could sort of intuit. You could say, well, it's not trigonal planar and it's not square planar, so it's between 90 and 120. You could do that, but no. Okay.
Dr. J, do you think they're going to give things like this on the sheet, or is this just something you have to memorize?
Okay, so yeah, we talked yesterday about that. So the way the AP test is going to work, you're going to get 45 minutes, and it's going to be all free response. Open notes, open Google. Okay, so you can use your computer for whatever. You just can't talk to anybody else. You can't have anyone help you. And you can use your textbook, whatever. And so you just got to be able to explain your way through concepts, basically, is what it's going to come down to as far as what I've heard from the College Board. So I think very conceptual. So you wouldn't see this exact problem because you could Google the ammonia bond angle, okay? But a lot of these other questions, like with the brittleness of the solid or the sea of electrons or whatnot. So these kinds of conceptual questions, you should absolutely expect to see and to be able to respond to.
Got it.
Mm-hmm. All right. So I don't know why I can't unlock the free response questions for you, but I'll go ahead and pull them up. Okay. So here they are. So N2 and N2H4. Okay. So all right. So basically you always want to show your calculations, right? And the way it's going to work on the AP test is that you can actually write your answer on paper, take a picture, and upload. So you don't have to type everything in, okay? So that's going to help us. You have to show your work, okay? You have to show work whether you're typing or using paper. Okay, so in the box below, draw the complete Lewis electron diagram of N2. And then is N2 polar? Okay, so this is a relatively quick question. I just wish you guys could work through this whole thing on your own because, like, oh gosh, I think this is the only free response question, huh? We just get this one question. Okay, so, all right, let's just do part 1 right now, and then I think I can scroll down to part 2. We'll look at that one, and then we'll do parts C, D, and E at once. So let's do part A and B right now. Okay, so in the box below, complete the Lewis electron dot diagram for N2. Okay, so do we feel like we can do that pretty quickly, or do we need a little time to do that?
Just N2? Yeah, we can do that.
N2.
Yeah.
Yeah? Okay, go ahead. Take like 30 seconds. Just knock that out, and we'll talk about it. And then I'm eventually going to let you do C, D, and E just on your own. I'm going to leave for a second because my dog needs to go out. So I'll take her up really quick. I'll be gone for like 5-ish minutes at that point.
Have fun with the munchkins.
Yeah, little pumpkins. I didn't get to take them for their walk this morning because it was raining. So she needs to go. I'll walk you later, Munchkin. Okay, about 15 more seconds. Just a second. Okay, so what did we get for N2?
I can draw it really quick.
You can? Okay, go for it, Caden.
All right. Very skilled graphic designer over here.
You're doing great.
There we go.
Perfect. Okay, Rainisha, did you get the same?
I just had one, but I had the two lone pairs, but I only had one bond.
Okay, so remember, right? These guys have to have access to 8 valence electrons through bonding. So like 2 lone pair electrons and then 6 bonding electrons for each nitrogen. That means 8, okay? Because nitrogen wants to be like its nearest noble gas, all right? So that's, what is that? That's neon. So nitrogen wants to be like neon, so it wants to have access to 8 valence electrons. But it comes with 5, right? It comes with 5. So like nitrogen has 1, 2, 3, 4, 5 valence electrons. And so all the unpaired electrons have to participate in bonds, right? And it's going to bond to itself. So you got these 2 nitrogens, right? With these, each with 3 valence electrons, okay, that are unpaired. And so they're going to bond, bond, bond like that. And that's why you get this structure here. Okay?
Yes.
Okay, very good. All right, so I'll erase the board. And then Bunch can hold on. And then, okay, you gotta go, I see. Go on, go cross the All right. So, okay, N2 molecule polar. Is it polar, guys? Is it polar?
Nope.
No, and why not? Rainisha, can you tell us why it's not polar?
N2 isn't polar because it's not sharing electrons.
No, remember, polarity is based on electronegativity differences. So will the 2 nitrogen atoms have different electronegativities?
No, because they're the same.
They're the same, right?
Yeah.
Exactly. Okay, the same atoms. They have the same electronegativity. Okay. And then, all right, so here's the graph. On the graph, indicate the distance that corresponds to the bond length of N2 by placing an X on the horizontal axis, okay? And then on the graph, which shows the potential energy curve of 2 nitrogen atoms? Carefully sketch O atoms. Okay, so O atoms versus N atoms. Okay, I see. Okay, so, okay, okay. So try C and D. Just think through that, okay? Give yourselves just a few minutes, guys. I'm sorry, but I'll be back as quickly as I can. This pumpkin just needs to go out. I'll be right back.
No worries.
Okay. And one more thing, guys, when you're ready, feel free to talk through this, okay?
All right, we'll do.
Okay, I'm gonna pause the recording.
Towards the bottom.
So right here is the most stable. Okay, yeah.
No, like right here, down. Yes, right there.
Yeah, right there. Yeah, right there. So like right here on the x-axis, because it said placing an X on the horizontal axis. So you put your X right there, right?
Yes.
Okay, cool. And that's the length of the end. Yeah, that's right. Because that's the minimal energy difference. That's right. So they come together and they want to bond like that. Okay. And then what would you do about 2 O atoms? What would you do about 2 O atoms? How would that work?
For 2 O atoms, I think it would, because I'm thinking, wouldn't it be relatively similar to the N2s?
Yeah, it would, right? But would it be, and where would it be though? Would it be higher, lower? Like, what's their distance going to be? Because think about N, right? N triple bonds to N, right?
Mm-hmm.
So to a first approximation, how does O bond to itself? Does it triple bond also?
No,
No, what does it do?
it double bonds.
Okay, so then you go O, like dot, 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 line, line. O, right? Okay. So that's your O, right? So what's longer, a double bond or a triple bond?
A triple bond is longer.
No, a triple bond is tighter, okay? It's a tighter bond, it's a shorter bond, right? So will the internuclear distance be greater or smaller for oxygen than it is for nitrogen?
It will be longer.
Longer, greater distance, right? So
Yes.
if nitrogen's is over here, then oxygen's, and I'll use red. So if nitrogen's is over there, right, then oxygen's is going to be maybe like over here, right? We don't know exactly what that distance is. Maybe it's going to be over that way, right? And then which one is a stronger bond? The triple bond or the double bond?
The triple bond.
Okay, stronger, right? So does that mean that oxygen's peak, that oxygen's minimum is going to be above or below the minimum for nitrogen?
It's going to be lower than.
You think it's going to be down here, right?
Yeah.
No, because it's a stronger bond. Or sorry, the nitrogen has a stronger bond than oxygen does. So oxygen's actually going to be less energetically stable, which means a lower minimum. Okay?
Yes.
Okay.
I see that. Yeah.
So like, yeah, so your oxygen curve, right? Your oxygen curve might look more like this. It might look more like, whoop, that was an eraser. I didn't mean to do that. It might look more like this, right? Like that. Okay, that would be a reasonable oxygen curve.
Okay. So Dr. J, was my understanding there that the absolute minimum here represents like its most stable orientation? Okay.
Yeah, that's
so
your bond
what is
distance. Uh-huh.
yeah. So what is the point where it crosses the x-axis here signify? Is this the point at which it's like, is that where is that like the amount of energy, the difference between there and here that is needed to break the bond?
Let me think. So basically, so the potential energy between the two atoms increases as their internuclear distance increases or decreases, right? So like here, they're just like on the right side, they're being pushed together too much. On the left side, they're being pulled apart too much.
Right.
It's a good question you ask about zero, though. I don't
Yeah.
remember off the top of my head. Let me see if I can like think my way through it. But I don't remember off the top of my head what the significance of the zero is. Like I've always thought of this curve as a relative construct. I've never thought of it as like an absolute construct such that zero had a special meaning.
Yeah.
I mean, I suppose you could define zero as the asymptote or the value you'd get if you just shove the nuclei together. I suppose you could define it that way.
Okay.
But I don't know exactly what that means because I've never, I don't think I've ever thought about that. I don't know if like I was ever in a lecture when one of my professors like talked about that. So I don't know like how physicists or physical chemists like define that zero. That's a really good question.
All right.
I'm trying to think about what it might mean. So you're pulling them apart, and at some point you get to zero, right? But then you're going lower and lower and lower than zero. So potential energy, right, just keeps getting lower. So it gets negative. I don't like. I think that just I think the thing that the zero indicates is that as these two atoms come together, they're releasing energy.
Okay.
So I think that's the important part. Like they're more stable together than they would be apart. But man, this is hard. I don't know.
Yeah.
I wish I had a better answer for you.
Okay.
Let me think about that some more.
Yeah, let's sleep on this and try it again tomorrow.
What that zero means. Okay. All right. But are we good on the rest of it, guys?
Mm-hmm.
Yes.
I'm gonna go ahead and erase the board. Okay. And then Kaiten, if you could do the same.
All right.
And then okay, on the graph, we already showed the O. And Kaiten, you were good on the O graph too?
Yeah.
Okay. So now we've got, okay, let's look at E and F. So a sample of N2H4 has a mass of 25 grams. Identify the numerical quantity that is needed to convert the number of grams of N2H4 to the number of moles of N2H4. You do not need to do the actual calculation. Okay. So need to convert the number of grams to the number of moles. Oh, what do you need? What is
You
what?
need,
Okay, just sorry. Think through it. Think through it. You can actually find that value. Okay, go ahead and find that value and just kind of discuss it, because you could totally be asked to do this. And then you've got this thing F. We'll do F in a second. So go ahead and take 30 seconds for E, and then we'll talk about part F. Okay, so what do we think here? What's the value we're going to need?
okay. So you're going to need the molar mass of the molecule, which is the sum of the molar mass of all the constituent elements.
Good. And then Rainisha, did you get that molar mass? Did you calculate it?
Isn't it it would be N2 like actual.
So what's the molar mass of a nitrogen atom? Do you have your periodic table open?
Uh-huh.
Okay, what's the molar mass of a nitrogen atom?
14.
Good. And how many do we have?
2. So
Right. So then
28.
calculate the molar mass of N2H4.
Let's see. So would it be 32?
Yep, 32. And what's our unit?
32 grams
Per what?
per mole?
Yeah, exactly. Okay. That's exactly what you need. Very good. All right. And that's what you got also, Kaiten, isn't it?
Yeah.
Mm-hmm. Okay. So part F, the Lewis electron dot diagram of N2H4 is shown below. Okay, there we go. Based on the Lewis dot diagrams of N2 and N2H4, compare the length of the nitrogen to nitrogen bond in N2 with the length of the nitrogen nitrogen bond in N2H4. Okay, so we talked about this a little bit ago. Go ahead and take like 30 seconds, just kind of get your thoughts together, and then we'll go through it as a group. Okay. So what do we think about this one? Who wants to get us started?
I can.
Perfect. Go for it, Renisha.
So with NH2 or N2, we know that it's a triple bond.
Good.
So
and
we know
triple
that
bond N, that's for N2. Okay.
And we know that triple bonds tend to be shorter.
Yeah, those are the shortest,
bonds.
Strongest bonds, covalent bonds, right? Good.
And we know that in N2H4, there's only single bonds
Single
made.
bond. Okay.
So therefore, they're going to be longer compared to NH or N2.
Good. Longer and weaker or longer and stronger?
Longer and weaker.
Very good. Okay. Kaiten, did you get the same?
Yeah, I got, so yeah, they're going to be longer and weaker.
Yep. Very good. Okay. Let's end that. And then let's move down. Strength. Okay. We already talked about the strength. That was part 2. Great. And the hybridization. Oh, like the SP, the SP hybridization. Okay. So I don't know how well we remember this, right? It's been a little while. Okay, give yourself like 20, 30 seconds just to think about it, and then we'll go through it. This is one of those topics we didn't spend a lot of time on, so go ahead.
I remember enough of this to remember wishing that I never have to deal with this.
It's easy. It's okay. I'll explain.
Yeah. Okay.
All right, so we've had a little time to think about it, right? Are we confused? Do we feel like we don't know what's going on here?
I do a little bit.
Okay, so let me just share a whiteboard with you and then I'll draw on it. Okay, so there's a whiteboard. All right, you guys can see the whiteboard, correct?
Yeah. Can I make a guess
Yes.
really quick here?
You can.
Okay, it's going to have 3 sp2 hybridized subshells.
Okay, let's talk about this. So we're going
Okay.
to start with a couple molecules, okay?
Right.
We're going to start with, let's go with NH4, or sorry, no,
Mhm.
CH4. So CH4, start with CH4. So CH4. Okay, the way this thing orients itself in space, right? You've got, what? CH4, so C.
Yeah. Dr. J, I can't see.
Yeah, I can't see either.
That's so weird.
Hmm.
Can you see it now?
No.
Nope.
I don't know why. Can you see it? No, why? It's like not working. Okay, so I'm gonna have to. That's so weird. Okay, let me just share my whiteboard then. Let me see if this will work. So. Okay, it works now, right? You can see the whiteboard now?
Mm-hmm.
Okay,
Yes.
that's so weird. Okay. All right, so let's just go with that. Okay, so if you have CH4, you've got C, H, and I usually like to, it doesn't matter, H, 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 like that. Okay, so this is going back behind the board, this is coming out of the board, and these two are in the plane of the board. Okay, so CH4 needs to arrange itself like that, right? But remember, an s orbital is like this, okay? It's spherical. And p orbitals are all 90 degrees to each other. They're
Right.
like this, and then back behind and back out of like that, right? Those are the p
Right.
orbitals. But this thing has this tetrahedral arrangement. So what gives? What gives is that the s and the p orbitals can hybridize and form these hybrid orbitals that are actually able to spatially arrange like this.
Okay.
So here we have 1, 2, 3, 4 of these sp orbitals. Okay, so we say that the s orbital and all 3 p orbitals are involved. So we call this hybridization. This is sp3. Okay, sp3 hybridization. Let's double check. It might not be a subscript too. It might be a regular. Like, this is one of those things. So it's just no. It's not even a subscript. It's just sp3. It's sp3, and those are lower cases, so it's sp3. sp3 like that. Yep. Okay. So sp3 hybridization. Okay, just like that. Okay. And you can tell that when you've got like basically sp3 happens around any atom that has a tetrahedral arrangement of electron groups. Okay, so like CH4 is sp3 hybridized. So is this other guy over here. So I'm going to draw like NH3, right? Ammonia. It's only making 3 bonds, but it's got 4 electron groups, one on top, one on the side, one coming out at you, one going back behind, right? So NH3, and that's an awful. Should be like that. Okay, there's NH3, and NH3 is sp3 hybridized too because it's got those 4 electron groups and they're tetrahedrally arranged. Okay, so that's sp3. Are we all good on sp3?
Wait, so Dr. J, is it good, or is it safe to assume that tetrahedral arrangements are most likely going to be sp3?
Yeah, if you see something tetrahedral, call it sp3. End of story.
Okay, got it.
Yep. Now let's take a look at something else, right? Let's look at this carbon. Okay, so you've got what what is it? Let's look at formaldehyde. So C double bond O, H, H. Okay, this guy's trigonal planar, right? Because we've got 1, 2, 3 sp orbitals, but we've also got this double bond, and that's just a normal pi bond. So that's going to be, when you see something trigonal planar, this guy is sp2. Okay, there's one of these bonds that's just a normal pi bond. Okay, that's just p orbitals bonding with each other. That's normal. The other ones, because they're in that trigonal planar arrangement, those are sp orbitals. So you've got 3 sp orbitals. We call that sp2. Okay, 3 orbitals total from the combination of 1 s and 2 p's. Okay, so that's sp2 hybridization. So if you see trigonal planar, think sp2. Okay, sp2. Okay, any questions about that guy?
No.
Nope.
All right, and it would really be the same, right? sp2 for bf3. If you have boron trifluoride, right, that's also sp2. Okay, it doesn't need that extra double bond to be sp2. It's just sp2 on its own, trigonal planar. Okay, and then let's talk about something that's going to be sp hybridized, 1s and 1p. So the way to do this is CO2. So you've got an sp orbital here. Okay, so CO2, I'll just draw it straight. So sp, you've got C double bond O, double bond O.
Mm-hmm.
And here's what that represents. That represents, you know what, actually I won't get into that because it's going to be brutal, but this is sp, okay? Because you have 2 normal pi bonds between this carbon and this oxygen and this carbon and that other oxygen, right? So that you're going to have 2 normal pi bonds, but you're also going to have some sp hybrid orbitals, like here and here, accounting for 1 of each of those double bonds. Okay, so there's a hybrid orbital there. Okay. So carbon CO2 like that is sp hybridized. Okay. Yeah. So an interesting question though is like, this guy is sp hybridized, right? This carbon, but like, what about these oxygens, right? What about the oxygen? Is the oxygen sp hybridized? We know that the carbon is sp, right? What about the oxygens? Are they sp or are they something else? So take like 20 seconds to think through that. What about those oxygens? Are they sp or are they, oh, that's interesting. Are they sp or are they something else? Okay, take just a little bit, go. All right. So how do we feel about this one? Rainisha, do you have anything to get us started?
I don't think it's sp. I think it's something else.
Okay.
However, I don't know what that something else is.
Let's take a look, right? How are the electron groups arranged? 1, 2, right? 3. What do we think?
It's, what's it, tetrahedral or not tetrahedral? What is the other one?
It's trigonal planar.
Good.
Yes,
So what does
that
trigonal
one.
planar mean, right? What did we say trigonal planar meant?
That, oh, go ahead.
Is that SP2?
Yes. Okay.
Okay.
SP2. All right.
So tetrahedral is SP3, trigonal planar is SP2, and linear is SP.
Linear is SP. Yeah.
Okay.
And that's the lowest you can be. You can't be like once you're no longer SP, you don't even have a hybrid. Like you don't have two hybrid. You can't have just one hybrid orbital. If you have one, you have to have two at least. Okay. They don't mix. There's no S. They're like that's it. It's SP. So our basic rules are okay. So this is our electronic geometry, and this is the hybridization.
Okay.
Okay. So if you have tetrahedral, you're SP3. Okay. If you're trig planar, you are SP2. And if you are linear, you are SP. All right. And that's your quick cheat sheet. So go ahead and get that copied down, and then we'll go back to the book problem.
Okay.
Or the AP practice problem, that is. Okay. So just let me know when you're done.
I'm done, Dr. J.
You too, Caden?
Mhm.
Can't hear you, Caden. Are you done?
Yeah, I'm good.
Okay.
The way I remember it is like the more messy and complex it is, the higher the SP hybridization.
Cool. And so here's Chrome. Okay. So here we go. All right. So the hybridization of the atoms in of the N atoms in N2H4. Okay. So what are those N atoms in N2H4? So go ahead and figure out what their hybridization is going to be. Take like 30 seconds. It should be pretty clear. All right, so what do we think, guys? Into H4, what's the hybridization of the N atoms?
Is it SP?
SP, okay. And what's our rule, right? What's our electronic geometry that we see for these guys?
If it's just for the N atoms and the also it counts for everything or just the N itself?
Just the N atoms, right? But how many bonds is this guy making?
It's making 2 bonds.
3 bonds, and it's got how many lone pairs?
2.
No, just two lone pair electrons, but 1 lone pair, right? So that reminds you a lot of ammonia, doesn't it?
Mm-hmm.
Right? Ammonia is basically the same way. Like ammonia, like nitrogen and ammonia, right? Nitrogen and ammonia looks like the same thing. It's like, except there's not another N over there, there's an H, right? But that's ammonia. What did we say about ammonia? What was its electronic geometry?
It's trig planar.
No, it's not trigonal planar. The electronic geometry, because there are 1, 2, 3, 4 electron groups. So not trigonal planar.
I forgot how you say the other one.
It should be in your notes. You were taking notes, right?
Yeah, but I don't know how to pronounce it.
Just slowly phonetically go through it. Tetrahedral. Yeah,
there you go.
Exactly. Yeah. Like I have to do that sometimes when I read really complicated words that I haven't seen before. I have to slow myself down. You know, like when we were going through particulate diagram, I was like, what does that really say particulate? Yes, it says particulate, particulate. Okay, I'm good. You know, like that's normal. Okay, so yeah, so this guy has a tetrahedral electronic geometry. Okay, and what do we always say? If we've got tetrahedral electronic geometry, what kind of hybridization do we have?
SP3.
SP3, okay. Does that make sense, Ranisha?
Yes, it does.
Okay, and what I'm gonna do next year is I'm gonna stress this when we do the Lewis structure stuff so that you guys see more of this hybridization business, because you could totally see this on your AP test, okay?
Okay.
All right, and we'll review this moving forward too. Kate, remind me if I forget, okay, to review hybridization, just like randomly start drawing molecules and asking people what the hybridizations are.
All right, will do.
Perfect, because they could ask you about that for sure. Whew. Okay. So scholars, any questions? We've had a really good day. I didn't think this would get us to 11, but indeed it has. So
Yeah.
last questions. I'm gonna stop this recording.
No.
Good.